Thank you for the presentation. So we're going to present our trip towards ratification of the control flow integrity specification in RISC-V, namely the shadow stack and landing pads. The outline for today's presentation is initially we're going to talk about what we are trying to defend against with this specification. Then we are going to describe the shadow stacks and landing pad extensions. Since this is a cross-stack, let's say we modified hardware, operating systems, tool chains, everything. So we will discuss the various modifications we were required to do, and also the Linux kernel support for this specification. So what is a control flow subversion attack? Initially, people just injected code in the stack or in the data, and because you didn't have any executable data prevention mechanism, you could just jump to the code you injected and execute it, and subsequently take over the system and do arbitrary code execution. At some point, there were some extensions that prohibited the execution of data from an application. So what the attackers did now were like, okay, we're not going to inject new code in the application. We're going to reuse whatever is already existing. One example is the return to libc attacks, where you just prepare the frame for a usable libc function that you could use in order to spawn a terminal, for example, and then divert the control flow by overwriting return addresses in the regular stack, and then execute the desired functionality. The other type of code reuse attacks, it's a technique which requires that the attacker finds usable snippets of code inside the application binary. This can be anywhere, and just change these together by overwriting control flow variables. This can be return addresses, function pointers, actually these two. So you chain these snippets of code together, and you form the exploit code. And then you can, again, take over the system. So what we tried to do with control flow integrity, it's an academically proven, let's say, principle for protecting against code reuse attacks or any attack that targets specifically the control flow data of an application. So we have a shadow stack where a function which says that a function may only return to its original call site, nowhere else. You cannot skip frames or return anywhere else in the code. So it protects against code reuse attacks that rely on overwriting return addresses. And the idea is that you store a copy of the return address whenever you call a function to an architecturally protected memory region. In this case, we have shadow stack memory pages. And before returning from the function, we compare the copy from the regular stack with the shadow stack copy. And if we have a mismatch, it may indicate that somebody tried to overwrite this return address and corrupt the control flow or take over the control flow. It can be a bug. It can be an exploit attempt. For the forward edge, meaning indirect calls through function pointers, what we did was mark the correct set of targets that an indirect call site can point to. To do this, we put labels in the valid code places. And so you set a label before the indirect branch on what to expect at the target. If you reach a point where you do not have the correct label, then somebody tried to divert the control flow. Again, it can be a bug. It can be an exploitation attempt. So the labels are set before the indirect branch and checked at the origin. To give an example on what happens, the original academic paper from Abadi was based on analyzing the control flow graph of an application. So you could enforce the control flow graph that you have analyzed the program and found. So without any control flow integrity, so any indirect call site, meaning function pointers or return, could point to any point or to anywhere in the code, anywhere. No, there was no restriction at all, except if you go to data and try to execute data where you will crash. And now there are many labeling examples, labeling schemes that we support, also in the shadow stack and landing pads, where we can have landing pads, so no labels at all. So any entry of a function is a valid target. Then you can have function labels, so each function is associated with a label, and then an indirect call site can point to only a valid set of functions. And then you can have call site labels, which are where you associate an indirect call site with an indirect call site now has a label which is appended to its, prepended to its function entry, to its valid function that you can target through these indirect calls. And the other thing we that has been worked on during this year is having function type based labels. So you can only point, if an indirect call site can only point to a set of, to only specific function types. So now Ved is going to discuss more on the hardware aspects of this specification.
Thank you. I'm Ved Shanbhogue. I'll walk you through. Thank you, George. For the next couple of slides, I'll walk you through the two extensions that we ratified here. The first one's called CFI SS. So CFI stands for Control Flow Integrity, SS stands for Shadow Stack. And what the CFI SS extension provides is the capability to have a shadow stack. So this shadow stack is a hardware capability that enforces the backward edge of the control flow integrity. In this parlance, backward edge is returns from a function. So effectively, the shadow stack holds a shadow copy of the return address. That's why it's the shadow stack. It shadows the stack. But unlike the regular stack, it does not hold parameters. It only holds return addresses. Like the stack, the shadow stack also goes downwards from a higher address to the lower address. And in the ISA, we define a new register called SSP, or the shadow stack pointer, that points to the top of the shadow stack. The shadow stack is, there's a virtual memory extension for shadow stack that defines a region of memory as a shadow stack. And the shadow stack memory has this property that only shadow stack instructions can write to that memory, and regular non-shadow stack stores are not allowed to write to that memory. That guards against inadvertent corruption of the shadow stack or the shadow return addresses that are held. We support turning on shadow stacks per privilege level, which also implies that your kernel can turn it on for itself, it can turn it on for the application, and it can context switch so that some applications may have shadow stacks enabled, others may not. So it allows you to mix and match and enable them in a gradual manner. It does not do away with the regular stack, and so it preserves the stack ABI while providing the shadow stack, and that's the reason why we do not try to elide the return address on the regular stack, but we keep a shadow copy and check it on the return, because there's a lot of software that relies on the stack layout and there being a written copy on the stack, and so we preserve the ABI. And the other goal was to minimize the static code size growth, and you'll see how we use compressed instructions to make use of that. So primarily, the extension provides instructions to do push and pop from the shadow stack to check the integrity of the return address, and for some common software management operations such as stack unwinds that are needed for software to operate. So let's look at the push and pop. So this is primarily two instructions. There's SS push that pushes the link register onto the shadow stack, and the SS pop check that pops the link register shadow return address from the shadow stack, compares it against the link register, and if they're not equal, that's an error, and it flags a new exception. We call it the software check exception, and there's a trap value that indicates that, hey, you had a shadow stack fault. So at the prologue of the function, you would have an SS push that pushes the link register onto the shadow stack. At the epilogue, you would have an SS pop check that verifies that the integrity of the return address is preserved throughout that function. And this push and pop is only needed for non-leaf functions. So if you're never going to spill the link register onto the stack, you do not need to spill the link register onto the shadow stack, and which is a nice property of shadow stacks, that it minimizes the number of functions that you need to instrument with shadow stack function. The next instruction that we provide is called ssreadp, shadow stack read pointer, and this moves the SSP, which is the new register, into an X register. So SSP otherwise cannot be encoded into the source or dest of any RISC-V instruction, but you can read its value using the ssreadp instruction. And this is useful for a couple of purposes. One, the encode, and I'll talk about how these instructions are encoded. When shadow stack is not active, the ssreadp will always write 0 to its destination. So it's a very convenient way of detecting whether shadow stacks are active. So for example, if you want to do write a common function in libc to do a stack unwind, now that libc might be invoked by a program that has shadow stack enabled, might be invoked by a program that does not have shadow stack enabled. How do I branch around the shadow stack unwind? You can very simply read, do ssreadp, and if it is 0, say shadow stack is not active, just skip the unwinding of the shadow stack. As I said, SSP cannot be encoded into the source or dest of any instruction, but you can read it. And you can also write SSP as a CSR. So you would see that as part of the unwind, you can write the SSP CSR. And we also provide some guidelines on how to do a safe unwind. For instance, you do not want to unwind past your shadow stack into the guard page into another shadow stack. And so there's a safe sequence that is specified here in order to do the unwind. The next main instruction that we provide is an instruction called ssamo swap. It atomically swaps a location on the shadow stack. And the main use case of this instruction is to be able to provide support for common operations such as stack switching. So when you're doing stack switching, be it in the kernel as part of the context switch, you need to switch from one shadow stack to another shadow stack, or in the user space as part of, for example, if you're doing uContext support and you want to switch shadow stacks. One of the common problems is, okay, while the SSP was in a register, it is protected, but when I switch stacks, I need to store the old stack pointer value somewhere in memory. If I store it in memory, it can be corrupted, and that would be an attack vector. So where do I store it? So we say store it on the shadow stack itself. And so we define this concept of a checkpoint, which is a shadow stack location that holds the address of its own location, value of its own address. And this checkpoint, you want to be able to save and restore atomically, so that if there are multiple threads trying to raise and restore the same stack, you want only one of the threads to succeed. And that's why the atomicity is important. So what this ssamo swap allows is to be able to save and restore these checkpoints onto the shadow stack in an atomic manner, preserving the security property of these operations. And later you'll see how we also use it for things like signal delivery. The shadow stack is protected from inadvertent corruptions using the virtual memory system. So we have a new PTE encoding. The XWR being set to 010 indicates that the page is a shadow stack. A shadow stack page allows shadow stack load stores. Shadow stack load stores are not allowed to non-shadow stack memory. It causes an access fault or a page fault. Non-shadow stack stores and instruction fetches are not allowed from shadow stack memory. You can read from a shadow stack, and that's a useful property because a lot of unwinders and tools like to know what the trace of return addresses is. And because the shadow stack does not have interleaving parameters and data, you can get a trail of return addresses very simply without having to have even frame pointers enabled. The shadow stacks, we encoded them using a new family of opcodes. We call them as MOPs, maybe operations. They're called maybe operations because normally they don't do any operation. So for instance, ZMOPs, those code points, they just write 0 to the destination. ZCMOPs, which are the compressed forms, just turn into no ops. But when the extension is implemented, some of these code points turn into the extension-defined instructions. And what that allows us is the ability to build a program with the shadow stack instructions in them. Now, they can be loaded on a machine that does not support shadow stacks. or it does not have an OS that knows how to turn on shadow stacks, and that's fine. These instructions will effectively turn into no ops, but the program will be compatible across this family of machines. And these ZIMOPs and ZCMOPs are mandatory as part of the RBA 23. That allows us a wide base of machines that are compatible for the program. So the developer does not need to ship multiple binaries. He can ship a single binary, and that same binary will be able to execute on systems without the extension. Of course, they won't get the security protection, but functionally, it will be able to execute. This is also useful when, say, an application is interoperating with the library is compiled with the shadow stack instructions, but if the program, the process has shadow stacks disabled, that's fine. You can continue to use the library. Those will just turn into no ops. Now let's look at the next companion extension. This is called ZI CFI LP, where CFI is control for integrity and LP stands for landing pad. There are two edges to the control flow integrity problem. The backward edge, which was the returns, where the attackers tried to corrupt the return address. We guarded that by providing integrity to the return address using the shadow copy on the shadow stack. Now for the forward edge, we need some way to say, if I'm making this indirect branch or indirect call, am I going to the right direction, right location? As hardware, we do not have that visibility, but now we provide this landing pad instruction that the compiler can emit, and the compiler is usually expected to emit them at valid targets of indirect calls and jumps, and that provides hardware the visibility. Yes, that is a valid point where indirect calls and jumps can land. We also provide the ability to associate a landing pad with a 20-bit label that is encoded as an immediate value as part of the landing pad itself. And so now you can add constraints that this indirect call side can only branch to this subset of landing pads which share the same label. Right? Now to track this landing pad, what the hardware has is a small state machine inside of it, which says when I execute an indirect call or an indirect branch, the state machine says, I expect a landing pad at the target. And when you decode the instructions at the target, if you do not find a landing pad, you will throw an exception. Or if you find a landing pad, but if it is misaligned or its label doesn't match the expected label, it will throw an exception and it will say it's a landing pad fault. If there is a valid landing pad with the matching label, then the program continues. This state machine goes back to saying, okay, no landing pad expected till the next indirect branch. To illustrate that, you can see this program here. It sets up the label in this X7 register. It says, I expect the label AABBC, makes an indirect call, indirect jump. In this case, if you land on a landing pad, all's good. If your label matches, all is good. If you try to subvert this indirect branch and make it land on an instruction later in the function, this is what attackers try to do. This will cause an exception. If you redirect it to a different function, which has a landing pad but a mismatching label, that will cause an exception. So it enforces that you must land on a valid landing pad. Now, as I said, there's a small state machine in hardware. So when the indirect call or jump executes, it sets that state to landing pad expected. But between the jump and the target instructions, a number of asynchronous events can happen. So you could take an interrupt, you might have a breakpoint, or you might take a page fault because the page that holds the next instruction is not mapped. In that case, we cannot lose the state machine state. And so if there is a trap in between the indirect call or branch and the target landing pad, then the hardware saves away the landing pad, expected landing pad state into a bit in a CSR, such as in this example, the trap is through the S mode, so it saves it in the S status CSR, and it sets the expected landing pad to no landing pad expected. The trap handler executes. When it S-rets, the ELP is restored from the CSR, and now the tracking continues, and the hardware says, I expect a landing pad, as if there was no interruption between the indirect call jump and the landing pad. With that, I'll hand back to George to talk about toolchains and ABI.
Thank you, Ved. So, of course, a lot of work has to be done for the toolchains in order to support the new instructions and the new capabilities we offer. So, regarding compatibility in hardware, push and pop shadow stack instructions, as we said, are defined in the new opcode space in maybe ops. So ZMOPs execute as NOPs if the specification is not active or it's not defined. However, many of the existing RISC-V Linux distributions and existing RISC-V cores do not have maybe ops yet. So shadow stack is going to cause issues. However, we can provide multi-lib in order to make it a multi-lib solution in order to support both of these variations with shadow stack and without shadow stack. And since in RV8 23 it is required to have ZMOPs as mandatory, sometime in the future, near future, it's going to be resolved by time. For the landing pads, since we use the hint opcode space, they already execute as NOPs in the existing hardware, so we do not have this problem. In software, the compatibility issues is how to deal with existing binaries and shared libraries. So you can add, so what we did was add a new GNU property in order to mark if an object is, can support shadow stack or landing pads or both. And then whenever you link an object, you can check if shadow stack or landing pads or both are available. So if you link something that has no support, you should disable the shadow stack for the whole process. So now, for the labeling scheme, we have labeled landing pads. Other architectures are just landing pads without labels. So we need to find a way in order to make a very performant, let's say, and pretty simple solution in order to mark the available spaces. Control flow graph would be ideal, but then you need to do very accurate control flow graph analysis, and then the compilation time is going to, especially for big programs, is going to skyrocket. For the first part, we cannot mandate people to use link time optimizations in order to provide a labeling scheme. Because this will limit the scope of landing pads. And there is a way to actually find similar types of functions, or in order to, let's say, provide a labeling scheme based on that I can point to, an indirect call site can only point to a set of functions with the same type, the same, I think it's the same format, actually. Yeah, so this is the Itanium mangling used in C++ ABI. But there is a problem. It is not designed for providing labels for control flow integrity. So we needed some simplifications in the mangling rules was required in order to support multiple inheritance, covariant return types, all the inheritance-related stuff in C++. Then you have different rules in different C++ standard versions. And of course, you have incompatibilities between C and C++ in mangling rules. Quito, who worked on these things, what they did is add some exception rules in order to make the labeling scheme compatible with all the different C++ standards and differences with C and all these issues on supporting symbol mangling for control flow integrity. So the Y component in the function type should be ignored, which is if it's a C or C++ function. The exception SCPC should be ignored because it doesn't offer any significant, let's say, insights for control flow integrity. And then for C++ member functions, they should use the pointer to member type. So instead of having the class name inside the mangled symbol, you should use the V type in order to have a similar thing across different inherited classes. And then class descriptors, again, should use the the void with void argument function in order to be similar, because it's the same, let's say, the same type, the same function type for nearly every object. So for then we added a new GNU property in order to mark if an ELF object supports shadow stack and landing pads. You can support shadow stacks or landing pads or both. There is no restriction on that. This is checked during dynamic linking. And for the labeling scheme, there is support for the unlabeled scheme, which is pretty similar on what control flow enhancement technology does. So you just only mark the function entry points with landing pad label 0. With a labeled scheme, with the unlabeled scheme, as we can see in the example, we have the LPAD 0, and then the function continues normally. We can have the function signatures-based scheme, so we hash the function signature and check that this is going to be set before jumping to main, and then we check it on main's entry point. Now, for optimizations, whenever we can remove, let's say, no functions target, no indirect call sites target a function, we can remove the landing pad instruction because it's not going to check anything. It's not going to be checked. We are not going to indirectly jump to this function. And then, of course, you need a new procedure linkage table format in order to support the landing pad scheme. So the PLT just loads the symbol address from the global offset table and jumps to it. With the unlabeled example, we just check that we jump to, whenever you jump to a function in the PLT, you just check that you land in a landing pad. And then when we have function signature-based scheme, we have to first check that we jump to the correct entry in the PLT, and then we set again the correct the hash of the actual function in the landing pad register, and then jump to the actual function. Now, for toolchain implementation, the status and plan as of September, I think, but I mean, okay. So there is a known standard version implementation of GCC. The unlabeled scheme is very close to be finished. The shadow stack is complete, and there is a patch in preparation. For binutils 2, there is a patch in preparation, as with glibc. There is no effort so far with GDB. And for LLVM, there is partial landing pad support, and there is a partial upstream version of shadow stack support for LLVM. And now we will move back to Ved for the Linux kernel support.
Okay.
Also, we have Deepak there if you want to ask him.
So yeah, thank you, Deepak, for putting the slides together. So in the next couple of slides, and I'm running up against time, so I'll be going fast. We'll talk about what kind of extensions we need in Linux to enable the ZI, CFI, SS, and LP extensions. Again, from a Linux perspective, Linux itself wants to use CFI for the kernel itself. It provides a strong security posture. With these two extensions, we can provide fine-grained control flow integrity. But at the same time, the Linux also needs to ensure that there is compatibility so that it can support intermixing of CFI-aware apps with CFI-unaware apps, and mixing of CFI-aware libraries with CFI-unaware libraries, and also enforcing user policies on when to enable and lock these capabilities. So when we talk about a program, we think of it as a monolith, but it's not really a monolith. There is a bunch of objects and binaries that make up a process. Just to show an example, you might have the app binary, which is what you're familiar with, PS, LS, and so on. But behind the scene, these app binaries, they depend on system libraries such as glibc, and they may also depend on other libraries, for instance, math library or some other pthreads library, and so on. And so an application depends on a set of libraries, and this application, and as well as the system library, the glibc. And all of these modules, they are loaded into the process address space by a special program called the loader, the dynamic loader, or the LD. Right? So LD is the one that runs when a task starts, and it looks at the dependencies of that application and loads the remaining dependencies into the address space. So once you have all these objects in your address space, there can be calls and returns happening across these binaries. So these may be synchronous calls, and there can also be asynchronous control flows. For instance, there might be signals being delivered by the kernel that lead to signal handlers being invoked, and the return from the signal handler going back to the application binary. And there might also be language-based, non-sequential control flow transfers, such as using set jump, long jump, swap context. We saw some of that as part of the extension discussion. So all of this poses a challenge for the Linux kernel to say, hey, when this, and for the loader to say, when can I turn it on? Because it has to evaluate all the objects that get loaded as part of the process and decide whether to turn on the extension for the process. And so what the LD does is it turns on shadow stack and landing pads if all objects that are loaded as part of the process are compatible with the extension. So it will look at the header marking. We saw that there was a header extension, ELF marking extension, to say whether the object has been compiled with the shadow stack or landing pads. And if they all match, then it turns on the extension. And what the kernel provides to LD is a set of system calls in order to turn on or turn off the extension for that process. The other main extension to the kernel is memory manager. It needs to create this shadow stack memory and set up the virtual memory system. So we ended up adding a new virtual memory type called VM shadow stack to identify the virtual memory region that is used for creating shadow stacks. Further, the kernel needs to handle the exceptions and faults related to the VM shadow stack, as well as deal with things like copy on write. To take you through a life cycle of a process, the first process starts up, let's call it init. The loader uses a set of process controls in order to turn on, say, shadow stack for this process. Now that process may fork child processes, and usually what happens is when you do a fork, the read-write segments, they turn into read-only segments, and that's because you want to do a fast fork, and these memories are shared between the child and the parent. And on the first write, you make a copy of that memory, and that's why it's called copy on write, and split the read-write segments. Now with shadow stacks, we have to do similar for the shadow stack memory as well, that when a process forks, we have to turn it into a read-only region and use the faults, page faults created on access to a read-only region in order to create a copy of the shadow stack for the child. The parent may create additional stacks, and so the kernel needs to provide a system call to create additional stacks, for instance, for threads in the process. And when you do an exec, okay, now your parent's objects are all gone, you're going to load a new program into that process, and LD starts all over again and decides what should happen to this new process. Now, I'll again skip through fast. So you got this concept of signals where the kernel can asynchronously change your control flow to a signal handler. We have a similar issue as to when you have this asynchronous control flow, how do you preserve the integrity of a shadow stack pointer? We use the same concept that I illustrated earlier about creating a token or a checkpoint and checking that the shadow stack pointer has not been tampered with when we resume from the signal handler. So to summarize, the Linux kernel enabling, it involves a set of extensions to the kernel for doing things like feature discovery, memory management, additional system calls, supporting context switching of the ZI/CFI/SS and LP state, exception handling, and crash dump and ptrace like debug support. So to summarize, we ratified the extension in July. We're very excited about this extension because it provides the most fine-grained CFI among competing architectures in the industry. We are also working to extend CFI to machine mode. So we are calling on member companies and people doing RISC-V implementations to implement the ZI CFI SS and LP extension. And we also call on our software colleagues to contribute to the toolchain, kernel, and application enabling. There's a lot of work to do, so please help us out.
Wow, give him a hand. I'll bet we can get 3 good questions before people get hungry. Any questions from the crowd? I do think there was a bug in your linking chart with all the libraries. You were missing an arrow somewhere in there. Here we go.
So question about the speculative execution. So when you task switch to a different process, do you make sure that the other process cannot guess what the previous process has done? Like you can maybe using the guessing what control flow has been executed by just manipulating the labels and trying different combinations. Is that even possible, or if possible, do you?
Yeah, the guarding against transient execution attacks is not a goal for this extension. For instance, being able to influence the transient control flow of a program through training the branch predictors is not what this extension tries to attempt.
But when enabling CFI, is it possible to enable the other?
Yeah, there are certain ways in which CFI does help. For instance, with the landing pads, now you can constrain where you can land even transiently, because if you have a missing landing pad, you can immediately stop execution, because you know
you're sure that this is not a valid target.
Right. So that allows you to contain speculation using the using the shadow stacks. You can say, if my return address stack doesn't have hardware RAS does not have a prediction, then I'm going to consume the return address from the shadow stack, not from the data stack. So there are certain things you can do, but that's not a first-class goal of the extension to guard against transient execution.
It's a byproduct, but very useful, actually.
Yeah. Great question. One more, Jose. Yes.
Thanks, Jeff. Gentlemen, thank you for the very clear and detailed presentation. My question is purely intellectual curiosity. Why did you choose this path to control flow integrity, particularly the shadow stack versus a cryptographic solution where you sign the return address and then you verify that the signature is valid?
Numerous academic publications. Seriously, I mean, we have been studying papers and proposals and everything. And so the shadow stacks are academically proven, and nowadays they are proven even in the industry. And also, if you have a signature, how many bits is this going to be? At some point, you are going to have problems with the entropy, and they had problems with the entropy in ARM. So
you were thinking probably of the ARM solution where they fit a 16-bit.
Yeah. I mean,
we do a 64-bit signature at power 10.
But
the advantage of the cryptographic signature is that the shadow stack doesn't capture recursion, right? Because when you're recursing and always calling the same thing, when you come back, you can skip levels, and you're still okay until you hit the beginning of the recursion, then you have a failure, right? But you don't capture the first fail, right? So the cryptographic solution, because it encodes the context, captures the first fail. The reduced entropy, I think I don't know why ARM did that way, but no, we didn't have to do it that way. We had plenty of space to put the signature, so we put a full signature there.
I took the microphone away so we could ask another question, Jose. But it's a good question. Why don't you chat with him afterwards? I want to ask one more question from the back.
They tried to fit it in the pointer. In ARM, they tried to fit it to be part of the pointer, so that's why they had this problem. But then you have to also use hardware in order to compute the hash.
Well, but the cryptography, there are some very low-cost cryptography that is quantum safe, right?
Okay.
As long as you don't go down the route of public key cryptography. Public key cryptography is a problem, but if you're okay with the secret key cryptography, it's not that expensive. Again, we did, full pipeline cryptography. It certainly was not the problem.
All right, Jose, let's go up here to this question.
sorry.
Last question. That's all right. That's all right. You guys can
we can,
continue
talk
outside.
offline.
Last question from the back here.
One question, is there also a recipe available to protect a shadow stack when memory is not translated? So no virtual memory?
That's for the M mode, actually. That's what, I mean, we have a point there. But yeah, if you don't have any available ways of protecting, of isolating a certain portion of the memory, then you cannot have a shadow stack.
No, so this is clear, but the question, I think you implicitly answered my question. So basically this work in progress to bring it to M mode will show a recipe on how to protect the shadow stack page or memory area when I'm running in non-virtual memory, right?
That's a goal.
Very good, thank you.
All right. Thank you, everybody, for your patience. Thank you to our speakers for your flexibility. Enjoy lunch.